Hello, I'm Melise Steyn, and I was part of the CSIR team that was responsible for developing a data architecture as part of a real-time information management system for the mining sector. Now, in a mine, a stope is known as the open space that is left behind when desired minerals have been extracted. These stopes can have sensors, meters, or actuators that can take certain environmental measurements or monitor conditions. This may include temperature, dust levels, oxygen, and energy pulse readings. Now, the data obtained from these sensors could be used to assist with mine-related problems or with informed decision-making. However, a quick response to changing conditions or sensor readings can only be conducted if these readings can be accessed from and analyzed on a local on-site computer in the mine. For more computationally expensive analysis and storage purposes, it may also be of great value if these measurements could be transferred to a platform in the cloud. So a main objective of our study was to therefore develop a data pipeline that would allow the flow of data from these sensors in the stope of a mine to other locations where the data can be utilized. We specifically focused on developing the pipeline to allow the flow of data between 3 different locations. First, the data had to flow from a sensor in the mine to a local on-site computer system where the data can be viewed or analyzed by someone in the mine. Furthermore, the data from the sensors had to flow to the cloud where more computationally intensive activities can be done and where data could be stored. Finally, the pipeline had to allow the flow of data from the cloud to these local on-site computers and vice versa. Now, since we didn't have access to actual sensors in the mine when this project commenced, we simulated data to represent readings from such a sensor. This diagram gives a short overview of how we created the pipeline to allow the data to flow from the mine to a local on-site computer and to the cloud. So first, the data had to be compressed to a smaller size before transmitting it and encoded to a language that can be understood by the different components of the pipeline. Since the data was simulated and no wired connections were available, a messaging broker was used to transfer the data from the sensors to an Internet of Things or an IoT gateway. So this gateway serves as the connection point between the sensors in the mine and the local on-site computers or cloud. All the information moving from the sensors goes through this connected gateway. Our pipeline was further expanded by connecting the gateway to a modular integration platform that is used to remotely manage the different devices, or in our case, the sensors that are connected to the gateway. The data was then finally transferred from the modular integration platform to the on-site computer using a streaming platform. On this local on-site computer, a user could now access, visualize, or analyze the sensor data in near real time. In a similar way, the data was sent from the IoT gateway to a data science platform in the cloud. On this data science platform, data visualization and exploration tools were implemented, where various tasks could be performed on the data. For instance, it could be used for analysis purposes, for visualization purposes, or even for training a machine learning model. After developing this data pipeline, the next objective was to develop a machine learning model in the cloud that would use the sensor data from the mine to assist in solving a mine-related problem. This could, for instance, be used to serve as a decision support tool or to provide an early warning system based on near real-time measurements from sensors in the mine. So the purpose of machine learning is to develop a model from historical data of the system under study with the aim of making predictions for that particular system from new, previously unseen data. The first step in developing such a model is to gather a suitable data set on which the machine learning model can be trained. We considered a data set containing seismic bump measurements at a mine in Poland. This data set encapsulates geological conditions in a longwall coal mine to determine whether a mine is subject to rock burst, which could ultimately result in a seismic hazard. So the data set consists of different kinds of readings, including hazard assessment results, energy pulse readings, the number of seismic bumps recorded within a previous shift, and then also a decision attribute, which is in this case listed as class in the sheet. Now, all other readings other than the class attribute describes conditions for a particular, or let's say a current shift, whereas the class attribute describes a condition for the shift following this particular one. For the class attribute, the number 1 indicates a hazardous state, which means that a high energy seismic bump, which is usually more than 1,000 joules of energy, occurred in the following shift, whereas the number 0 refers to a non-hazardous state where no high energy seismic bump occurred in the following shift. So the objective of this part of the study was to develop a machine learning model to determine whether a hazardous state can be expected in the next shift by considering the geological measurements of the current shift as input. Now that we have identified a suitable training set, the next step was to develop a model. For this study, a classification type neural network model was considered. As input, the model would be given the geological conditions of a particular shift, which consists of that shift's energy readings, seismic bumps, pulse readings, etc. The model would then give a classification as an output. So this classification would either be a 0 to indicate the non-hazardous state in the next shift, or the number 1 to indicate that a hazardous state can be expected in the next shift. Now that we've trained our model on the seismic bumps data set, we can now use this trained model in the mine. So the current shift's energy, pulse, seismic bump readings, all of these measurements which the model has never seen up to this point can now be fed to the model, and then the model will predict whether the next shift contains a hazardous or a non-hazardous event. After testing the performance of the model, we found that the trained neural network would generally predict a hazardous or a non-hazardous instance in the next shift with an 86% accuracy. So what does that mean? It means that for every 100 seismic events, the model would accurately classify about 86 of them as hazardous or non-hazardous. Right, so a machine learning model that predicts whether a hazardous seismic event would occur during a following mining shift based on the previous shift's sensor readings has now been developed and trained in the cloud. We then sent this newly trained model to the edge, which basically means that the trained model was now available on the local on-site computer system in the mine. The data from the sensors could now be sent directly to these computers, and the model could, in near real time, predict whether the next shift would consist of a hazardous instance or not. So what would the person sitting behind the computer in the mine see? We visualized our model's output as follows. During each shift, the model would consider the measurements and the readings in the current shift and make a prediction on whether the next shift would contain a hazardous instance or not. If the shift did not contain a hazardous instance, the number 0 would be plotted, or at the 0 it would be plotted. If a hazardous instance was predicted, a 1 would be plotted. On the x-axis, the time of the current shift is given. If the person in the mine therefore sees that a hazardous instance has been predicted for the next shift, that person can look at this table on the left and see what probability did the model give to that instance actually occurring, and then make a decision on what to do next accordingly. So in conclusion, we've developed a data architecture for data to flow from a sensor in a mine to a local on-site computer, as well as to the cloud. We've also developed this architecture to allow the flow of data from the cloud to these local on-site computers and vice versa. And then finally, we've developed a deep learning model in the cloud that would use the sensor data from the mine to assist in solving a mine-related problem, and deploy this model on the local on-site computers in the mine so that predictions on new data can be made in near real time and necessary decisions can be made timelessly. Thank you.